In the last class, we are looking at interaction between radiation and convection. And we considered a very simple problem of a flow over a flat plate, and we looked at a very elementary example where the flow was inviscid, that is effects of viscosity were not important, and the gas was gray. This is of course a very ideal example, not related to real world, but it illustrates clearly the role that radiation plays in convective heat transfer. So, it is a way to illustrate in the classroom. So, the flux, the radiated flux is varying in the y direction and the flow is going in the x direction. And the radiative flux variation in the y direction was written in terms of tau, the optical thickness is nothing but A into y, where A is the absorption coefficient. So, if T wall is the wall temperature and you consider a black plate, then the radiative flux all of you will recall will be 2 sigma T to the power of 4 E3 of tau, where E3 is the exponential integral function representing the angular integration, plus the radiation from the gas below a given layer and radiative flux from above the given layer, and we go to infinitely thick region there. So, this is the radiative transfer equation and the corresponding energy balances So, this is the energy balance equation that we are trying to solve, of which the QR expression is right here, but in order to work in a non-dimensional plane, we transform both the x coordinate and the y coordinate to non-dimensional form. Y coordinate is already non-dimensionalized by the absorption coefficient. The x coordinate is non-dimensionalized as follows: 2 sigma A T infinity cubed x by rho C p infinity, where we have linearized equation, because remember that convection depends linearly on temperature, while radiation depends temperature to the power of 4. So, if you want to get a simple analytical solution, you need to linearize the rate transfer equation, and once you linearize it, you get the following expression for the energy balance. So, this expression was obtained by linearizing the radiative transfer equation and differentiating it. And if you look at the expression, you will find that the important parameter that comes into play here is the relative role played by radiation versus convection, and we will now solve the equation. Now, in order to solve this equation, Before that, we will also mention what is the wall flux. The wall flux is a very important expression that we need to obtain. So, that can be written as ratio of the wall flux without radiation, without convection, and that will come out as this. So, once you solve for theta, you substitute here, you get the wall flux. Now, the standard way to solve this problem is what we had already discussed earlier, is the exponential kernel approximation. Okay. And in this case, we will take a slightly different form than what we used earlier. E1 of t is assumed to e to the power 2 e to the minus 2t, and E2 of t is e to the minus 2t. Now, the way this approximation has been done, that E2 of t is a good approximation at t equals 0 here, because it is 1, but E1 of t at t equals 0 should go to infinity, but we have taken only value 2. Now, this is still a good approximation, because this goes into the integral, and when you integrate E1 to give E2, then you will find that it will not really affect the answer too much. So, once you have done this, your expression for temperature becomes so, this is the expression that we have for variation of temperature after it is linearized and we have done the kernel approximation. Now, to solve the equation, we apply a Laplace transform. Many of you would have used Laplace transform in transient conduction or convection problem, and the transient term here really is psi here, because it involves psi is related to x and u infinity, and it is essentially a virtual time coordinate. Now, Laplace transform of theta, it becomes theta bar, it is a function of s and tau, and by definition of Laplace transform is 0 to infinity theta of psi, the time-like coordinate. So, this is how we transform theta of psi and tau to theta bar of s and tau, and then you apply the standard rules of Laplace transform for differentials and so on. You get this expression. This is the boundary condition, which gives you 1 at time t equals 0, and the right hand side becomes theta 8 e to the power of minus 2 tau 0 to tau theta bar e to the power of 2 t dt plus 8 e to the power of 2 tau tau to infinity theta bar e to the power minus 2 t dt. And if you now apply the kernel approximation, that is differentiate twice, and eliminate the integral terms, you will get the following differential equation for theta. So, this is the final expression you get after Laplace transform and kernel approximation and eliminating the integral terms. And one can show very easily that the solution to this equation, ODE really, ordinary differential equation, is 1 over s plus c e to the power minus 2 tau root of s by s plus 8. Okay, where the constant c can be shown to be over s. Okay. So, this simple ODE, and so this is the non-homogeneous term where theta is taken as 1 over s, not a function of tau. So, this term drops out, you get this equal to that, and this is the solution of the homogeneous equation. Now, you need to transform this result into the psi coordinate. So, you apply inverse transform. After applying the inverse transform of Laplace expression, which is available in many textbooks, you get the following result for theta. This is the Bessel function, or more correctly the modified Bessel function, and this is well known and is available in most textbooks. And once you got that, you substitute back in the equation for flux, and you get the flux at the wall, which is what we want. In terms of two modified Bessel functions, and so you can see that we have been able to obtain an analytical solution for the radiative flux at the wall and the temperature distribution in terms of exponentials and the Bessel function. Now, if you want to understand what this psi can be rewritten in terms of the conduction radiation parameter which we discussed earlier, the length scale, and what is known as Peclet number in coordinate transfer. N is an expression where n we are already defined as A into k by 4 sigma T infinity cube, which came up in the conduction radiation problem, k the conductivity, and Peclet number is nothing but u infinity x by alpha. So, finally, the functional dependence of temperature and flux depends upon the conduction radiation parameter here in terms of absorption coefficient, in terms of the conductivity of the gas, Stephan-Boltzmann constant, and temperature of the gas in infinity, and the Peclet number. And as you can see, in the limit of a very large Peclet number, this quantity becomes very, very small, and you can think of simple results for the convection transfer, and you should be able to recover some of the solutions we obtained last time for radiation and convection based on series approximation. So, series approximation is valid when psi is very small. So, when psi is very small, that is the n is very large or Peclet number is very large, then this becomes very small. Then we can expand this I0, I1 and e to the minus 4 psi in terms of linear terms, and then you will get the result which we had obtained earlier using the series approximation. So, this is a more general result valid for all psi, and so you can look upon the result which we got in the last class as a special case of the result for the here, which is a Gen solution which combine Laplace transform and the kernel approximation to get the solution valid for all psi. And so, only weakness of this solution, if you look at it, is the gray gas approximation, which will limit its use for any practical application. But still, if you want to get a quick idea about how strongly the convection influences radiation, this is the starting point for you to decide whether you want to do a more accurate or a more elaborate calculation of interaction between radiation and convection. Now, just to give you a flavor of the kind of effect this result has, well, let us look at Nusselt number. All of you heard of Nusselt number, which is a non-dimensional measure of the heat transfer coefficient. In this case, the Nusselt number will be defined by H x by k. Okay. H heat transfer coefficient, x is the horizontal scale and k is the conductivity of the gas. And many of you would be aware that for laminar flow over a flat plate, this is typically comes out as 0.332 when there is no radiation. So, if there is radiation, this is going to be modified. The question is, how is it modified? If you plug those numbers into the expression we are given just now, you will see that when psi is very, very small, it will start at 0.332, because that is in the limit as radiation being unimportant. And as you go to larger and larger psi, it goes on increasing, and when you reach psi around 1, you can reach a value around 0.6. So, what radiation does is modifies the temperature distribution such that the gradient of the temperature near the wall increases by almost a factor of 2 when the psi increases from a very low value to 1. So, this is a good way to get a rough idea about the impact radiation on convection. And so, in a given problem, if you want to decide whether you have to account for radiation, you should be able to estimate the value of psi for the given situation, and if the psi value is indeed of the order of 1, then you should realize that the Nusselt number or the heat transfer coefficient by convection can increase by almost a factor of 2 in the presence of radiation transfer. So, this kind of simple analysis is useful in dealing with problems which are in which there is some interaction between radiation and convection. Now, in all the problems we have done so far, we have neglected scattering. So, we are always considered only a non-scattering medium. So, that is a serious limitation, because there are many examples both in engineering and in atmosphere, where the presence of particles, liquid or solid, tend to scatter the photons, that is, photons change direction. So, that was not incorporated in our discussion so far. We had assumed that the gas was a pure absorber and not a scatterer. The reason why scattering is treated near the end of this lectures is because it makes life very complicated. So, a photon which is traveling in one direction encounters a particle, and that particle now will change the direction with which photon is going. So, the presence of particles in a medium fundamentally alters the direction of movement of the photons, and that makes the geometry problem much more complicated. Remember that So far we had deal with a non-scattering medium, and we could generally treat directional effects through some kind of kernel approximation, in which you took a mean direction and calculated, and we got very good answers as we saw just now for the convection problem. But when the scattering is very important, then you cannot treat directional variations very casually. You have to worry about those things. So, we will now look at scattering. Now, before we get into the basics of scattering, let us now first discuss what are the scatterers that are present. The smallest scatterers are molecules, obviously, and molecules have dimensions of the order of 10 to the power of 4 micron. So, their effect is not really very large except at certain wavelengths, we will see that. On the other hand, there are things called aerosols, which are liquid and solid particles in the atmosphere or in the combustion chamber. So, to one example, and their dimensions are typically of the order of 1 micron. Since the dimension of the aerosol is about 10,000 times larger than the dimension of molecule, it has higher scattering effect. Even larger types of scatterers are droplets, which can easily go to the size of 10 micron if it is a liquid droplet, rain droplet for example. And then you come to ice particles. They can be of even larger dimensions than the ice droplets. And finally, we have hail or large raindrops. And these can easily reach the dimension of the order of 1000 to 10,000 micron. So, what you find is that the particles that are there in the gaseous medium that we encounter either in engineering or atmosphere in the Earth's atmosphere can range in sizes from 10 to the power of minus 4 micron to 10 to the power of plus 4 micron. So, huge range of particle sizes, and as you will probably realize, their effect on the radiation are different. And the typical example that we will look at now are, if we consider A as the particle diameter, and lambda is a wavelength of light which is being scattered, then if the wavelength of light is much smaller than the particle diameter, the scattering is isotropic, independent direction. So, this is the easiest case to deal with, because you do not have to then worry about directional effects. On the other hand, if the wavelength of light is much larger than the particle dimension, this happens in the case of molecular scattering of visible light. Then what you get is what you must have heard of in your physics classes, called Rayleigh scattering. And this is something which you have heard about in your earlier courses, and we will discuss this further. And finally, if the wavelength of photon is comparable to the dimensions of the object concerned, you get what is known as Mie scattering. So, what I want you to appreciate the fact that if the wavelength of light is very small compared to the dimension of the object, then life is very easy. Scattering is pretty much isotropic. So, we will show that the treatment of isotropic scattering makes the problem very, very simple. On the other hand, if the wavelength of the photon is much larger than the dimension of the particles which are scattering, like the molecules. So, if you have visible light and which is of the order of 0.7 micron and molecule of the size of 10 to the power minus 4 micron, obviously lambda is much greater than A, and you get the standard Rayleigh scattering, which we will discuss a little later. But many cases that you encounter both in engineering and in the atmosphere is where the wavelength of the radiation is comparable to the size of the particle, in which case you have Mie scattering, which is the most complicated. This is the most complicated case, and this is most difficult to calculate, and until the advent of the computer era, this problem was not easily handled at all. And today, of course, because of the available computers, you can handle Mie scattering quite easily, and involves a lot of calculations, but these calculations are fairly straightforward. Now, let me now illustrate how we handle scattering in a simple way before we go on to more accurate treatment of scattering. Now, we have defined absorption coefficient. And absorption coefficient was, if you recall, related to the fact that the intensity along a certain path was minus A lambda I prime lambda. This is how we define the absorption coefficient. Now, when absorption and scattering occur together, then the attenuation is both due to absorption scattering. So, we need to add one more term in the attenuation term. This is scattering coefficient now. This is absorption coefficient, which we had discussed earlier, and the combined thing is called the extinction coefficient. The extinction is a sum of absorption scattering. So, photon can disappear from a given direction either because it is absorbed and is gone, or it has been scattered and hence does not appear along the given direction. So, extinction can be both either due to absorption or due to scattering. Now, the units of absorption coefficient, all of you know, is meter minus 1. So, that is the same unit for the scattering coefficient, but scattering coefficient also has got other standard ways of defining in terms of cross section. So, this is scattering cross section defined in terms of scattering coefficient, which has units of meter minus 1, and volume, which has units of meter cubed. So, this gives you meter squared. So, cross section is a very popular term used both in nuclear engineering as well as in radiation, and it has a physical meaning. It is the effective area that the object offers to the incoming radiation, effective obstruction in some sense. So, many people prefer to use cross section, but we prefer to use absorption coefficient and scattering coefficient, because both absorption coefficient and scattering coefficient, when you take the inverse ratio, you get the typical photon mean free path, and so that is a convenient way to understand the role of the photon. Now, I will give a simple example of the Rayleigh scattering, which all of you have heard about in your physics courses. Rayleigh scattering occurs when visible light is scattered by molecules, and that scattering coefficient there can be written in terms of volume of the scatterer and the refractive index of the particle. So, this is a fairly well known expression for the Rayleigh scattering, showing that the Rayleigh scattering goes as 1 over lambda to the power of 4, and many of you have heard that this is what makes the sky blue in color, because the molecules of atmosphere which scatter the sunlight, which is in the visible 0.4 to 0.7 micron, tend to scatter the if you look at VIBGYOR of sunlight, there is more scattering of violet light than red light. So, more from the white light, a lot of violet is removed, and what is remaining is red, and that partly will explain during sunset why you see a red sun, because during sunset the amount of particle molecules between you and the sun is much larger, and many of the photons in the violet, indigo, blue, green and orange are up to green are removed, and so the sun tends to look more more orange or red in color. So, Rayleigh scattering is a very simple example, but remember this Rayleigh scattering works only if the diameter of the object is much smaller than the wavelength of light. So, it only applies to scattering of light by molecules, but if you look at all of the particles we discussed, like the scattering by soot particles in a furnace, scattering by liquid droplets in the atmosphere, scattering by ice particles, there this equation will not be valid, because we cannot satisfy this condition that the radius of the particle is much smaller than the wavelength of light. In such a case, you have to deal with Mie scattering, and so in Mie scattering you expand, your problem is that the radius of the object is comparable to the wavelength of light. So, the Rayleigh scattering value is the leading term in an expansion, one, and then you have many more terms which you have to deal with. So, there will be a series of expansion terms, many terms, and higher the value of pi a lambda, you take more terms into account. So, this is a fairly difficult expression to calculate, slowly converging, infinite series, and so this calculation normally is very time consuming. So, you will not find simple results for Mie scattering in any textbook, because it is much more complicated equation to that we have to deal with. Now, another problem that comes in scattering, which we do not normally consider, is whether the scattering is by a single particle or multiple particles. As you can imagine, the scattering of a single particle is very easy to take care of. There is only one particle and the photon is influenced by that particle. If there are many particles in a given volume, and if they are very close to each other, then there can be interaction between the particles, scattering by each particle with other. So, the expression we gave here for both Rayleigh scattering and Mie scattering is for a single particle completely isolated, then this expression is easy. But if there are many particles, then the photon scattering from one particle will come and interact with another particle. So, the problem is much more complicated. We will not have occasion to look at such complicated cases, but you can rest assured that today, because of the availability of computers, you can actually tackle this problem in a computational a proper software that is used for computation of these complicated scattering cases. Now, let us look at how the basic equation of transfer is fundamentally altered by the presence of radiation. So, we started with our basic equation of transfer for radiation. And if you recall, this expression was as follows: for a non-scattering medium to begin with. So, this is the expression we use for a non-scattering medium. Now, if you have a scattering medium, this expression is substantially changed. First thing we already had indicated, the attenuation term is enhanced by scattering function. This term, emission term, will not change, that is always there. And there is one more term, what is called scattering in, that is the photons from other direction are scattered into a given direction of interest to you because of the presence of scattering, and this is written as sigma lambda by 4 pi times g lambda, where g lambda is defined as 2 pi 0 to pi So, we are neglecting the changes in the phi direction, it is only the theta direction we are concerned with. So, essentially this term is going to add photons. What is happening is, you have a photon which can be scattered out by a particle, that is the first expression. The photon from another direction can be scattered in this direction also. So, this is a term which adds to your intensity, because photons traveling some other direction has been now scattered into the given direction of interest to you. And the expression we wrote can be rewritten in terms of what is known as single scattering albedo, which is the ratio of the scattering to scattering plus absorption. If it is a non-absorbing medium, then omega lambda is 1, purely scattering medium, and if it is a highly absorbing medium and this dominates over that, then omega lambda is tending to 0. This is a pure scattering medium, omega lambda is 1, and this is a pure absorbing medium where this is much smaller than that. Now, with the definition of this single scattering albedo, we can rewrite our equation for intensity where kappa lambda is nothing but sigma lambda plus A lambda into ds. So, the extension coefficient, and so now we see the expression very clearly showing the role of attenuation of absorption. This is the emission term and this is the scattering term. So, we see that in a non-scattering medium, omega lambda 0, this goes away, this goes back to the original expression, but in a medium which both scatters and absorbs radiation, we are now linking the intensity in a given direction wavelength to not only to the incoming intensity and the intensity of emission by a black body is also related to another expression called G lambda, which essentially connects all the other direction to a given direction. So, this is what is going to make our life very difficult vis-a-vis solving the equation, because in the previous approximation we had made where in network scattering, the photons traveling in the other directions did not affect our result. So, we are merely concerned with photons going in a given direction. They were either attenuated by absorption or they were enhanced by emission or by scattering in. But now, the last term is going to bring in the effect of all the other direction on the given direction. So, when there is scattering taking place in a given situation, the complexity of the problem goes up many times, because now we have to worry about solving the direction spectral intensity in all the other directions in order to get the answer in a given direction correctly, because they are all coupled through this term. So, this term is the most difficult term we have to deal with, because it links the intensity in a given direction to intensity in every other direction. So, when we deal with scattering in more detail, you will find that we have to pay much more close attention to the directional nature of the radiation, because the intensity in a given direction depends upon the integral of radiation from all other directions. This linkage was missing in the case of pure absorbing medium, in which the scattering was negligible. There, the intensity in a given direction was not linked to intensity in other direction. So, we could treat the angular integration in radiation rather casually, but now we cannot do that. We have to account for it very carefully. Now, in spite of these complications, we can still argue that in the thin limit, when both the scattering and absorbed code is small, one can still calculate the flux as from surface 1 minus surface 2. So, whether it is scattering or whether it is absorption, both are very, very small, and you of the thin limit you can use that. And in the thick limit, you can use the Roseland diffusion model for a scattering medium. So, you can see that in very simple cases, in the thin and thick limit, you can easily extend the simple models for thin and thick limit to include scattering by merely modifying the A lambda to A lambda square lambda. But in all other cases, we are going to be having a difficulty because we have to, cases where the thin and thick limit is not valid, we have to take care of angular nature of radiation extremely carefully. And so, this will be the part of the discussion in the subsequent lectures as to how we tackle scattering problems in which the effect of other angles is felt in a given angle. Now, I can write a more complicated expression to explain what happens in the scattering medium. So, the last term which we wrote in a simple way G lambda can actually be written as sigma lambda. You have to worry about two directions, 0 to pi and 0 to 2 pi, that is the azimuth angle and the other angle, and this sigma lambda 4 pi, this part we all know. So, you are worried about the I prime lambda in the direction different from your direction, and the probability of scattering from theta prime phi prime to theta phi, this is the key expression, times sin theta prime d theta prime d phi prime. So, this is the expression which decides how a photon traveling in a given direction theta prime phi prime lands up in your direction because of scattering. So, scattering is linking the radiation coming in the direction theta prime phi prime to radiation in the direction theta phi. Now, this linkage was missing in the pure absorption problem, because in a pure absorption problem, we are merely concerned with photons in a given direction being absorbed by gas molecules or scattered out. There was no scattering in the pure absorption problem. In the scattering problem, this term which due to scattering change the direction of photon from theta phi prime to theta phi, that is what causes a lot of complication, because in order for you to solve for I prime lambda theta phi, you must know accurately what is the intensity in some other direction theta prime phi prime. So, you have to link the intensity of radiation at a given angle of interest to you to the intensity of radiation in any other direction that is there. So, all radiation problems in no scattering demands that you solve the scattering equation very carefully, because any simple approximation that you make for the scattering term must be carefully considered, because unless it is isotropic scattering, which is a very rare case, in all other cases the scattering problem is going to make life very hard. Okay. Now, we will illustrate that issue of how scattering influences your answer by a simple example here. So, before we go further into the example, let me write down the expression for radiative flux in a absorbing scattering medium. This is essentially the extension of the derivation which we did earlier for pure gas radiation. And you will see that in addition to expressions we had earlier, simple expression we had, we will have now much more complicated expression which relates QR lambda. If you recall the first term that comes from the wall, so I will put 2 here, and this is from the bottom wall, 0, and the top wall will be at tau 0 lambda. So, first the radiation from the bottom wall has to be integrated over all angles, and take into account attenuation. So, this is same as what we did earlier. This part is not anything new. Okay. Similarly, second expression for the top term is minus 2 pi, again 0 to 1 I minus lambda tau 0 lambda mu e to the power of tau 0 lambda minus tau lambda by mu d mu. These two are essentially same as what last time. Now, the two expressions involving emission will also involve scattering terms. We have 2 into 0 to tau lambda. We have an expression for in terms of kappa lambda by kappa lambda plus sigma lambda. So, this is the absorption coefficient by the scattering coefficient, and so this expression now will be kappa lambda by beta lambda, okay, where beta lambda is kappa lambda plus sigma lambda, and that involves E lambda b, that is the emission term, plus, so let me just write it in a clear way so that all the expressions similar to what we have seen earlier. Kappa lambda I will write in terms of A lambda, so that there is no confusion in the notation compared to what we used earlier. So, the ratio of absorption to scattering plus ratio of scattering to absorption plus scattering times the G of lambda, which is the expression which involves the scattering term, and the entire thing is of course multiplied by E2 of, and finally, the last term 2 tau lambda to tau 0 lambda, and this will be similar. So, I will not write it down, and E2 of t minus tau lambda dt. Okay. So, I want you to see how the original expression for radiative flux, we did not have these two terms, now has two additional terms inside the integral now. And what makes this very complicated, as all of you will appreciate, is because there is an additional unknown. This was already unknown in the problem, which is the unknown temperature distribution of the gas. Now, this is the unknown distribution of the intensity in the gas. So, you have to solve for both, and so the problem gets an order of magnitude more complex, because the way you treat angular variation now is much more critical than what it was in the case where there was no scattering. So, basically the pure absorption emission problems were much simpler to deal with compared to what we are now deal with when we look at combined absorption and scattering. So, there will be much more heavy mathematical derivations to take care of that, and so problem becomes a lot more complex and much more difficult to interpret the physics of the problem. This we will take up in the next lecture.